Hi, in this video I'm going to talk you through how we can code up the fourth-order Runge-Kutta method in MATLAB and use it to solve an initial value problem. Okay, so the first thing we do is we use the keyword function because we're defining a function in MATLAB, and our outputs are going to be an array of t and an array of y values. And we're going to call this function RK4, which is a standard shorthand for the fourth-order Runge-Kutta method. And this is going to have four inputs of f, which is a function containing the ODE, which we're solving, t-span, which is an array of two values, which is the start and end point of the t-domain, y0, which is our initial solution, and h, which is our step length. Okay, so within the function, I'm going to determine how many equations we're solving, how many ODEs, which will be defined by how many values are in y0, so I'm going to call this m, and n steps, this is how many steps we're going to need to step through. Okay, and this is simply the difference between our two t-span values divided by the step length h. And notice here I've used a floor function to round this down to the integer below. Okay, and now I define arrays of 0 for t, which is going to be n steps plus 1. Okay, so this is simply 1 for the first value in t-span and n steps for the rest. And for y, this is similar, but I'm going to have m columns in y. So for each sort of equation in our system of ODEs, we have a column in the y array as well. Okay, and to start these off, I define the first value for t to be the first value in t-span, and the first row of y is equal to our initial solution y0. So the next thing we do is use a for loop to step through our steps of the Runge-Kutta method, and we calculate the stage values. Okay, so I'm not going to go through these in this video here, but the Runge-Kutta methods use intermediate stage values in the calculation. So k1 is always the same, tn f of t and yn. K2 onwards can be slightly different depending on what Runge-Kutta method you have. Okay, so I'm coding up the general sort of standard fourth-order Runge-Kutta here. Okay, and for these coefficients, you can either look them up or check out the lecture notes. Okay, and yn1 plus h times k3. So those are our intermediate stage values, and now we use those to advance the solution to the next step. And this is our current solution plus h over 6 multiplied by a weighted sum of our stage values. Okay, and we also have to update our t array, and the next value of t is equal to the current value of t plus the step length. Okay, so this is our fourth-order Runge-Kutta method function coded up. So above this, so remember in MATLAB, any functions which you code which have to come up at the bottom of any script. What I'm going to do now is define an ODE and solve it, and call this function solve it. So before I do that, I'm just going to clear any memory and clear any workspaces. So this clear, nothing's in the memory at the moment, as you can see from here, and clear CLC clears this command window down here. This is just good practice before you write any MATLAB script. So the first thing I'm going to do is define an ODE function. I'm going to call it f. I don't have to call it f. That's just a standard thing. So that's this function here, and I'm going to return t times y. So this is a very simple example from the lecture notes. This is quite an easy, simple ODE function. If you had a more complex one, you'd probably want to define it using the function keyword. The next step is to define the initial value problem parameters. So what we're going to do here is we're going to use a t-span of 0 to 1, an initial solution of 1, and a step length of 0.2. So note with the initial solution, I put it inside an array because we use m equals length of y0 here to determine how many columns we have in our y array. Okay, so if I had it just as a number, when we try and calculate length, it might return an error. Okay, so that's the initial value problem defined. So now we just need to solve the initial value using our RK4 function. And to do this, I can just copy and paste the function declaration. Okay. At this stage, what I'm going to do is just run it to see if there's any errors. There are no errors, but what I do notice here, even though I don't need these columns, I have a load of columns or empty columns here, and this is because I haven't specified how many columns in the T array. So if I run that again, you can see our T array is just a 1D array. Okay, what I like to do is actually print a table of solutions, just so you can check your solutions. And to do this, we're going to use fprintf commands. Okay, so this is standard print statement. So I'm going to start off with some column headings, and I'm going to edit these depending on the width of the table in a minute. Okay, I'm going to use a for loop to loop through all the values in T. And for each value T, I'm going to print out the values. So in MATLAB syntax, the percent says, okay, we're going to output a number, and for T, I'm going to output it to say 2 decimal places, and for Y, I'm going to output it to say 6 decimal places. So this percent 8.6f, this means whatever float we're going to output here is going to take up 8 character spaces, with 6 of them being after the decimal point. And that's going to be Tn and Yn. So if I run that, you can see it's just outputted it all on one line because I did forget to do a \n for a carriage return. Okay, so there's our table. Let's space out the T and Y a bit better. We've gone a bit far there. Okay, this is just purely cosmetic, doesn't really matter that much. Okay, so this is our table of our solutions. So we've got our excuse me, our T array or values of T and our solution by default for the Runge-Kutta method. Okay, finally what I do like to do is plot the solutions. Okay, so to do that, it's quite easy in MATLAB. It's just the keyword plot of T against Y. And I'm going to plot using a blue line with markers, circle markers there. So each point in this table will be marked with a circle. X label, what I'm going to do is use T. So this is a horizontal label. And if you notice here, I put LaTeX commands in. So we need to tell it to interpret them using LaTeX. And I'm going to introduce the increase the font size to 16. And do similar for the vertical axis. So there's going to be YT. So it's going to be LaTeX and font size. Oops. Can't spell equals 16. Okay, so if I run that now, you can see we have our printed. That's our solution there. A couple of things which I'd like to improve here is I don't, it's the first point is right on the border of the plot, and also these individual markers are kind of hollow. So what I like to do is just to change the markers. I'm going to say if I just move that slightly to one side. So if you use marker face color, okay, and I've got it in blue. So if I rerun that, you can see we've got filled in markers now. And another little trick is if you use axis padded and run that, you can see it kind of zooms out the axis slightly so we can see the full plot.